And alright, here we go. Hello, hello. Welcome to the stream, everyone. I'm sure this was very sudden for you. This is not my usual time. Wait, I have to rescale my window here. There we go. Yeah, this is not my usual time, and didn't have a proper announcement beforehand, but this was a bit sudden for me as well. I had some free time, and even if you know, people wouldn't join live, at least I wanted to do this while I had some free time and have the video available later on, because that would be a nice reference to have. So small background about whatever we're gonna do today, and yeah, lately I've been crossing some effects of my shader bucket list. Last time it was volumetric effects like volumetric fog and all that, which was something that I wanted to do for a very long time, and afterwards I really wanted to understand how screen space reflections work. Oh, hey, welcome to the stream. Yeah, I wanted to try and make some screen space reflections essentially and figure out how they work, and you know, then go on and make them work well and look good and all that. But to my surprise, this turned out alright. Oh, hey, tough nut to crack, welcome to the stream. So yeah, I recently shared my results here. This is all screen space reflections, so all real-time reflections, but very artifacty, mostly because, you know, they're screen space, so if something's not in the screen, it's not reflected. But it's such a neat concept, and I managed to make this kind of very intuitive, at least for me. So I would hope that it would, this video and this stream basically would serve as a good intuitive solution as to how you can, well, not do this. I mean, you know, if you can understand what's going on here entirely, that's awesome. But you know, it will also give you like a good understanding of other effects, mostly more about ray marching. Thanks for the follow, KNTC. Yeah, because as I mentioned, I got into ray marching lately, and yeah, I'm hooked. I want to ray march everything now. And it came to my attention that screen space reflections actually worked with ray marching, and we'll get into how exactly these work and how I made this, because, well, pretty much I'm gonna be making this again from scratch, because this is I'm not using the post-processing stack here. This is just like classic, just a graphics blading thing. Like, I was so bored that I even used like the ray marching script that I had for the volumetric fog beforehand, so I didn't even make a new script for it. It's all contained in one shader, which is nice. But the cool thing about this approach and this process is that we can actually use it later on. So for this effect to work, we do need the deferred rendering path. Like if I set this to forward, it doesn't work anymore. But it's also good that we're using deferred, because we can actually take advantage of this in the deferred shading path. So, alright, let me try and draw some things for you. Alright, so let me paint. There we go. Alright, let's see if I can give you a good idea as to what's going to happen here. Can I... No, I cannot skew this, right? Is there something like skewed? No. Okay, whatever. I'll just play around with lines. Lines will work fine. So, let's say we have... Oh, yeah, okay. Paint is nice. Alright. So let's say we have this kind of... wait. Yeah, alright. Perspective. Yeah. Alright. Yeah, alright. Let's say that this is our ground. Alright. And we have our camera. Let's... Wait, no. What? What? No, stop. Okay. And we have our camera. Why is it green? Stop being green. Yeah, no way. People don't use paint no more. but I'm too bored to open up Photoshop. Anyway, and let's say that we have our camera right here. I mean, let's give it a nice little orange thing. Okay, let's say our camera is here. As you know, cameras is not, we'll just represent it with one point right now, but you can imagine that it actually is shooting rays all over the place using the view direction, frustum, mouth, whatever. But let's just say that it's 1 point right now. All right. So basically, what happens here? Can I make it dotted? No. Okay, I'm asking too much. We're shooting a ray, right? Let's make this. Oh no! You know what? Let's keep it orange. Let's say actually that we have like a little thing to reflect here, right? And we want to draw the reflection of this circle, sphere, whatever. I mean, yeah, I can paint it in. Yeah, whatever. Okay. So we could expect that there would be like some reflection of this on the ground somewhere around here, right? I mean, I'm just making it fuzzy because it's a fuzzy reflection. I mean, it's blurred and it's just a reflection. So how do we get that? All right, let's say that we want this pixel. This, I just drew like a small pixel here, like this pixel, which is gonna get this color. Our camera is gonna fire a ray from its origin towards this pixel, and we can get the world position of this pixel. You might see some implementation using view space, coordinates and rays and all that. I prefer world space, it's much more intuitive. I can assume it has its problems. Whatever, it worked for me, and I just wanna just get the logic there. Okay, so we can get this position right here. All right, and the cool thing is that because we're in deferred, we can also get its world space normal. So this point is gonna have like a normal going like that. Ooh, I can make it an arrow. Like this. All right, this is the normal. So since I have a direction and a normal, I can just reflect that ray. But why? Okay, let me redraw the normal. Redraw. Okay. All right. Stay there. Stay blue. Thank you. All right, and I can now reflect that ray, and let's just say there's perspective here. Let's just say that this is a perfect reflection, right? And now I can shoot a ray towards this general direction. And the thing is, we can start ray marching from the world space position, and we can, go with a constant step and move through space, and then whoops, we're gonna hit something. And we can compare whether we shoot something using the world space position and the position that our ray is currently. And we can check that we hit something, then we're gonna do something, it's a binary refinement just to get as close as we can, which is handy. And then we can sample this pixel right here, and we can get the UV coordinate of our screen and just map it here. And because our screen is red at this point because we have the sphere there, if we get that coordinate and put it there, then that's gonna be red as well. So it's a really cool thing because we don't really need to care a lot about reprojecting stuff based with perspective and all that. I mean, it's just, we're just playing around with our UV coordinates and wall space. I feel it's very intuitive. At least, you know, I basically fumbled around and, you know, tried to make it work. And after everything, you know, it seemed pretty intuitive to me. So I hope that it will seem intuitive to you as well. But obviously, feel free to, you know, ask away if you want any clarification whatsoever. I'm drinking coffee. It's early. All right, don't judge me. All right. So first off, what we want is for this to go away. So go away, like deprecated image effect. Hey Mitch, welcome to the stream. I'm gonna turn on post-processing. So this is Unity's screen space reflection implementation on the processing stack. As you can see, there's a lot of smearing going on, which is it's to be expected. It's a classic thing happening with screen space reflections. Hopefully my implementation, as you saw, won't have these. It might look a bit better, but either way, I mean, you know, just getting the logic should be fine and interesting. So let me just yeet this away. All right, and let's start making the script first off. So I'm just gonna call it screen space reflections. I mean, custom screen space reflection, because, you know, I don't want to get in the middle of just the built-in screen space reflections. All right, by the way, I started using Rider. I mean, I'm still you know, using it on a trial basis. It's amazing for shaders. I'm still getting used to some autocomplete stuff and like a lot of the warnings and messages, but I'm loving it for shaders. Like, it has everything. Like, and now for work I use URP. So just writing shaders and being able to, you know, dig through all the include HLSS files, this is fantastic. All right. So let me just reopen my grayscale post-processing. As I mentioned, I think I did mention that in the previous video, I'm using it as my reference script. Oh, like it's independent scaling. That's cool. Anyway, as I mentioned, I'm still figuring out Rider. Visible. Process type of reflection renderer. Post-process event before stack, and it's gonna be under custom. Yeah, I have already set it to VS Code shortcuts, and yeah, it has helped a lot. And you can see I've already taken the liberty to add like particles. And to be fair, the particles from the Power Mode plugin here are much more pretty and intense than VS Code, so, you know, I'm happy. All right. What do I need? Honestly, nothing. I mean, you know, I can just have like, no, nothing. Screw it. I won't have any parameters. I mean, it's gonna make my life easier either way. So let's seal this up. Reflections, set, sorry. Process effect renderer of type cut from screen space reflection. Yeah. Okay, remember. Oh, yeah, it would mention missing members. Okay. See, it's yet. SSR and context command delete full screen triangle. So there is a command buffer here, but that might come in handy. But let's keep things simple for now. Rider is awesome, but only Chrome is allowed to eat all my RAM. Oh, I haven't noticed any RAM hiccups yet from Rider. I probably will. Here, render this. Oh, that's cool. Anyway, yeah, no, I won't go in there. I mean, this seems like a bad idea. Anyway, all right, and let's make our shaders. Just gonna call it. You know what? I'm just gonna duplicate grayscale if I can find it. No, it's okay. I'm just gonna copy again. So, SSR. SSR, because I already have the SSR from my previous tests, so just calling it custom SSR. And you know what, let me just change it here. Through that and through that. Let's see things going. Reflections, awesome. All right, effect is hooked up. I don't need those anymore. Oh, I have to zoom in on every file though. That's annoying. One thing I also love about Rider is hot reloading without having to change the window, and you can see like already like when I save, things change behind my editor, which is cool. All right, let's see if I have all the things I need. So, did I end up using that? No, I did not. We have some things open as well here. There we go. All right, so let's see if I can indeed sample my normals, because these will come in handy. So gbuffer texture 2 basically handles, stores all the wall space normals, right? So if I just sample texture 2D, I mean, yeah, you can see it already auto completes way more stuff. For example, take depth texture LOD. Cool stuff. Cool stuff. Camera with sampler. Yeah, I think. And let's see. Awesome. Like you can see already, things are here. Though, something to keep in mind is that I should unpack that. Or, you know, just do this to, yeah, properly get the right normals, right? Because when they're in the G buffer, they are remapped so that they are, you know, they're going from 0 to 1. And we want this to be accurate because like right now you can see, right, the up vector is very green. It's like intense green. Like even if I don't know if you can see that, but yeah, like sampling the color is very green, so you know, up. All right, I switched to water now, no more coffee. And yeah, you can see that there should be some, okay, here, yeah, red is this way, so this is right, and blue is here. Yeah, you can see it's like very colorful and proper, and you know, all the good stuff. I should, you know, I should also get the first. I mean, I should get the first as well. So in the first G buffer, we keep specular color. I might not use that, and smoothness. I might use that. And oh, you know what? I might expose some stuff after all. Did I end up using this? Oh, I did end up using that. Okay. You know what? I'll do it first with some constant values, and then go in and, you know, maybe expose them as parameters. Another thing I'm gonna need is obviously depth texture, because I want a way to sample wall space. Yeah, let's pick some things here. I'm copying some stuff from the volumetric fog effect. Sorry. All right. Yeah, so I'm gonna need this, and I'm gonna need pretty much the same exact vertex method. Right, let me confirm. You know what, I'm just gonna... I don't think I'm gonna use anything from here, so might as well, instead of this, let's just use the vertex ID directly. So resolve symbol. Did I include something? No, I think it should be able to resolve that. Just making sure. Camera inverse projection. And what do I call this view dear? Why can I not resolve that though? Oh, alright, I just need to add that here. Oh, and thanks for the follow roll. Yeah, alright, it's compiling alright now. And I get my view direction, but you know what, I'm gonna rename to Ray. Also, this is cool, I can rename variables in shaders here. Yeah, awesome. Alright, I don't need any orthographic stuff, so that should work. And let's see if I can now get some world space position. Also, let's change that to convert. No. P to F. Yeah, because I want V to F, and this should be UV. And work. Awesome. Still working. All right. Basically, this is how things are gonna go. I'm just gonna break things and then make them work again. That's the process. And all right, let's try and get here. Let's add some methods. All right, so oh, you know what? Let's I don't have to do that. So let's try and get a world space position here. World plus it's gonna be Oh, I've been looking into the wrong shader all this time. Right, compute view space position, screen to wall post, wall to screen post. All right, yeah, okay. This is good. This, all right. All right, so I'm gonna need this method. Okay, I'm back. All right. This is straight from K0's inverse projection thing to basically compute wall position from a screen position. What doesn't it like right now? Couple depth texture. Am I doing something wrong here? Depth, some depth texture. Oh, it needs a sampler. And now it should work. Awesome. All right. And I'm gonna need some extra methods here. So this is gonna give us a view space position from a UV coordinate. Now I want a screen to wall position. Just gonna take the ray and the float to UV, and it's gonna return more inverse view from execute view space position, array UV. It's a position, so I want the fourth component to be 1 and XYZ. So, okay, turns out I'm gonna have to pass some extra parameters here and there. So, am I using this? Yeah, am I using this though? No, I don't think I am. So, I'm gonna need these two additional matrices. So I can go and get those real quick. Sheet. Wait. Context set. Okay, I forgot about grayscale. It's sheet properties, alright. Sheet properties set matrix, and it's gonna be the inverse view. It's gonna be the context camera to world matrix, and sheet properties set matrix. The view section matrix is gonna be the context camera non-jitter predict, yeah, all that stuff multiplied by camera. Context camera multi-camera matrix. These are the ones I want, right? Yeah, view projection inverse view. Yeah, these are the ones. So, are things still rendering? That's cool. So now, wait, why are things still rendering? Okay, yeah, whatever. So, position, it's gonna be screen to world position with i.ray with i.uv, and let's say that color .rgb is gonna be a price of the world pulse. And let's see what's going on here. Okay, I think, yeah, that looks good. So everything's stable, everything's proper. You can see moving things around seem correct. So yeah, these are in fact world space coordinates. You can see that there's some flickering here because it's exactly at 0 on the Y and the X and Z. So, you know, frac is just going around 0 and 1 because precision. But you can see, yeah, it's looking good. And you can also see that if I actually git the frac, this is the origin, right? 0, 0, 0. So this is all accurate. Great. All right. So we have our world position properly. So now I also want a way to get a screen position from a world position, like the opposite thing. So this is gonna be another method which we're gonna use a lot. It's gonna be called world pos to screen, or you know, just world to screen pos. That only takes a world position, and we need to get the projected coordinates. These are easy to get. So new projection matrix for world pos and 1, right? And the UV is gonna be xy divided by projected coordinates w, projected perspective correction. And this essentially what's going to happen, it's gonna convert a world space position to a clip space position. But clip space is actually right in the middle, and it's going from -1 to 1, and we want to remap it, so we're gonna multiply by 0.5 plus 0.5 and then return. than that. Alright. And just to see that things are working, let's do a quick test. So let's just say that the color is UV 01. Alright? Alright. You can see we get default UV coordinates, right? This is 0, 0, this is 1, 1, it's just UV coordinates. Alright. If now, instead of this, I convert my world space position back to screen position, I should get the exact same thing, right? Because I'm using my UVs to get a world space position, and then I'm reprojecting that over back to my screen, so it should be the same. So if I say world to screen pos and give the world position, then nothing changes. Alright? That means that we can go to world position and back to screen position properly, and that's the key thing. That's basically all there is to it, to the whole difficulty of the thing. Just figuring out how to go back and forth to different spaces, so that, you know, we can then compare things. Alright, alright. And let's... Alright. Let's get this started. I have my wall position. That's cool. I also need... I also need my world normal. So let's get that. Normal. That's it. I have my normals here. I want my camera position. I mean, that's easy. World space camera pos. Yeah. Alright. And I want the direction of the ray that we're gonna, as I saw, you know, basically it's this direction here, this one here, which we have this direction, right? It's if this is X and this is C. This direction is easy, it's just, you know, X minus C, you know, and then we can normalize that. And if we want the direction going from X to, I don't know, let's call this Y, which is the target pixel we want to go, then this direction that we want, this one right here, is gonna be well, basically it's just the reflected one from the normal. So, you know, if this is the normal vector, right, we wanna reflect this vector along the end. So flow tree ray here is gonna be, let's normalize everything though. Normalize the reflect of normalize again. World position minus scan position along the normalize normal. Let's just world normal. Let's normalize everything just to be sure. All right, and this is our ray direction. This is it. This is our D. Let's just call it R. All right. Alright, we have this going on. Alright. We can do some things with smoothness now, but let's not get into that. So let's just declare some constants here, just to we can convert them to parameters later on. That's why I'm gonna write them as if they are parameters, and so later on we can just replace those easily. So yeah, we want what the step size is gonna be and how many steps we're gonna take during the array marching, the maximum amount of steps. The maximum distance that we want, the reflection to be visible is gonna be like 100. These are all the numbers that I used on my demo beforehand, by the way. The number, let's make it uint, of binary search steps. Oh, hi Sasha, welcome to the stream. I'm just gonna take 5 binary refinement steps, and the thickness, this is gonna be very handy for eliminating some of the smearing artifacts. Sorry, let's make it like this. It's gonna be 0.1. All right. For now, smoothness, we can sample from the gbuffer 1, but for now, you know what? Let's say that it's 1. All right. We can use the smoothness to actually fake some diffusing in the reflection direction by basically just randomly jittering it around, so it looks as if if we actually blur the reflection, it's gonna look more diffused. But for now, let's keep it 1, because why not? All right. So the distance traveled is gonna be 0. We start, with no distance traveled. If you watch the previous stream or have any idea about ray marching from the camera with like volumes or ray marched geometry, it's pretty much the same concept, but instead of actually shooting a ray from the camera and just ray marching along that ray, we start ray marching at the reflection point, so basically at the wall space position that we sample at this specific pixel. All right, so we want that to be 0. We want the previous distance. I'm gonna use that somewhere. I'm gonna use that for you know what? I'm not gonna write it down yet. You know what? It's just I'm gonna write it down. And the previous point distance, am I using that? No, I don't think I'm using that, so screw that. All right, I want the color, gonna be 0. And I want my target UV coordinates. This is all like a game on the UV coordinates. I'm gonna start with my UV coordinates that also I can comment that out. Yeah, I can start with my default UV coordinates here. Finally, mask. Do I need that? No, I do not. Again, that's unnecessary. And depth gonna be all right. So yeah, because I just fumbled a lot to get things working, I have some redundant code in there. So I want a visibility thing, which is gonna be one. Weird that I do it there. Anyway, yeah, it's gonna start as 1, and it's basically to mask out some of the reflection so that we get less artifacts. And let's start. Wait, before that, and let's have another value, let's call it depth, which is starting with the value of the thickness. All right, and let's start ray marching. So j minus the max amount of steps, j plus plus. All right. We want the previous distance to be the distance that we have traveled, and after that, the distance we have traveled, we can increase by step size. Step size. All right. The position we're currently now is the world post, the position that we started, so like the world space position, plus the ray direction multiplied by the distance we have traveled. So, just going on along the ray with a fixed step. And this is gonna be, we can just call it ray pos, just to make it even more clear. This is the position that our ray is currently, all right? And we also have our projected position, all right? This is gonna be the screen to wall pos, the ray, and the wall to screen pos, the ray position. So, what's going on here? Let's draw something again. Wow, it's drawing with space as well. That's annoying. Anyway, so let's say that our camera is here, all right, and it's setting a ray. We're gonna make it lighter. Setting a ray down there. All right. This ray is gonna reflect like that, for example. We can, if we wanna draw the normal vector, it's gonna be this way. All right. And this is gonna be the direction that our ray goes, right? So let's say that the first step it takes is here. Let's say that this is like the distance of our step, the size of our step, which like I have defined to be 0.1. Let's say that this is like 0.1. This is however much it needs for the first step. All right. As you can see, as you can maybe imagine, this ray bounced off, and this position is on the air, right? It's not hitting anything. So what we want to do is reproject this point back to our camera. So let's change this here. So we're reprojecting that position in screen space for our camera, and using that screen space, our camera is gonna try and get it's gonna try and get the world position that it's seeing at that world space coordinate, and we're gonna get this point on the plane, right? Because the I don't know if you can see that, but because the ray bounced off into the air, so it took like this point along the ray, and it shot from the camera to get the world space position, and it found the world space position that matches this screen space coordinate that happens to be on the plane, right? So what we want to check now, we basically want to check the distance from the camera between these 2 points. So let's do that. But first, give me 1 second, I will be right back. All right, I'm back. Sorry for that. Okay, where were we? Yeah. So yeah, I was talking about getting the projected position back from the array position. All right. And we can get the projected position distance. This just gonna be the distance from projected pos and com pos. All right, and we can also get the distance from the position along the array. So array pos this is gonna be the distance from the array position to the camera position. So again, going back to this lovely graph. So this is, if this is the actual position that our camera is seeing when, you know, sampling from the projected position, this is the projected distance. So PD, projected distance, and this is the array distance, RD. All right, so if the array distance happens to be larger than the projected distance, it means that we ended up hitting something, right? So let's do this check. So we can call the depth now, we can call it the position distance, array position distance minus the projected pos distance. And we can say that if the depth is larger than 0, which means that the array position distance is further away than the projected distance, it means that we hit something along the way, right? Because it means that is this ray matching from first principles? What do you mean first principles, bewilderbeast? So yeah, because if let's say on the 2D way, right, we have our camera here and we have a wall right smack down here, right? I think it started from nothing. Yeah, it's from scratch, right? And you know, we have the ray going here, so let's, you know, ignoring everything else like the reflection and all that, if the ray position here is, if the distance, from the camera to, from the origin, whatever, to this ray position is larger than this, which is the point where we actually, you know, hit something. If it's larger, then, you know, we are behind something, we hit something. If the ray position is smaller, then we haven't hit anything yet. All right. So let's say this it's gonna make a lot of sense. You know what? It's here and here and here and here and so on. And this is like, you know, every step of the way, right? With every step of array marching. All right. So we hit something, and if now this is to eliminate some of the artifacts. The depth is smaller than the thickness. Then we hit something, right? But the thing is, let's say let's actually make it ridiculous, right? So let's wow, okay, this is all right. Let's make this extremely ridiculous. So let's say this is our wall, right? And you know, we know that this is our camera. This here is our camera, or whatever. This here is our camera. We're throwing down the ray that way. All right, and let's say that these are the steps, right? Let's say we have really big steps. So here and here and here. I mean, I know these are not proportional, but let's just say that these are the steps. All right. So what's going on with the binary search, the binary refinement? This is like something that actually kind of scared me when I was on other SSR implementation, but it's really not that big a deal. So when we're here, we check the distance from the camera from this point and from this point and this point, right? And you know, it's smaller, so we haven't hit anything. That's cool. We keep going on. Now we've hit some, and now we know that this distance is larger than this distance, right? That this point is further away than this point. But we don't know exactly at which point, you know, we hit that. We just know that, you know, we're past the point that we wanted to hit. So we want to close that gap, because like this is quite a big gap. We want to kind of close it and just get as close to the position as we can, just so, you know, we don't have very inaccurate reflections. So let's call this P, all right, for the position, and let's call this P hyphen, or you know what, let's just call this P1, which is the previous position, the previous distance, and let's call this P2. All right, what is going on with the binary search is really simple. That's why I kept this previous distance here, so I can get this point again. So now I have the distance to this point and to this point, so I can actually get the distance between those. Now I happen to have this be very close, so let's sorry, to be very in the middle, so let's try making it just so it's clearer. So let's say that the wall is actually here, right? So as I am getting the middle point between the two, it's gonna be somewhere around here. It's actually again after the point that we want, right? So now we try to get the middle point between the new point, let's say it's P3, and P1, and the middle point is somewhere around here. We see that it's less, so we want to get the middle point between P4 and P3. It's gonna be somewhere around here, and we keep going on as much as we want. Right now we have like 5 steps, so we're gonna do this basically 5 times, and that will, you know, get us pretty close to the actual point. So that's the whole point of the binary search and the binary refinement. So let's do that. So from another loop. So if the k is smaller than the binary search steps, k is plus, then we get the midpoint distance. Midpoint distance. It's gonna be the distance traveled plus the previous distance multiplied by 0.5. Right? If I remove all these, the previous distance is this, the current distance is this, so getting the middle point is gonna be, yeah, somewhere around here. Does that make sense? I think it makes sense. So we have another distance now, and we want to get the ray position at that specific point in the middle of these two other points. So again, it's gonna be the same thing we're doing here. So wall position plus the ray direction multiplied by the midpoint distance at this time, not distance traveled, midpoint distance, because we want the middle point. And we do exactly the same thing as we did before. So we get the projected position, which is gonna be the screen to wall pos, with, you know, our ray and the wall to screen pos of the ray position. So again, we're trying to get the projected, we're getting this projected position. Now, to be fair, and somebody might point that out, I just now realized that I don't need to re-get the projected position, right? Yeah, because we know the projected position already. So let me just comment that out, and if I notice anything weird, I'll just add it back in. But that's probably an unnecessary calculation, because yeah, it doesn't, since it's going along the ray, the projected position will never change. It's gonna give us the same UV coordinate. So if the distance between the projected position, we still had it from before, and the camera position is less or equal than the distance of the ray position and the camera position. So again, if the projected position, so this one, yeah, so if we're again further away, yeah, if we still hit the surface, essentially, we wanna change the distance traveled to be the midpoint distance, and we wanna store that UV coordinate, because we want the UV coordinate as long as we have hit something. That's the point. We don't want the UV coordinates if you haven't hit something. So that's where we store that. Wall to screen pos, and we get the ray position. Otherwise, we just change the previous distance to the midpoint distance. And either way, after all that, we break, because we have found a position. We don't want to keep searching. That's all. All right. Again, if anything is not clear, if you wanna ask, you know, why I'm doing things the way I do them, just let me know. Of we change every step as you iterate down the ray. Will it though? Because yeah, it will, sorry. Yeah, you're right. On my example, it was a straight line, so in a straight line, it doesn't change. But you're right. Yeah, you're absolutely right. So yeah, just keeping that in. Alright, so I haven't done anything for the visibility right now for any of the masking, so you know what? Let's try and see what's going on here, right? Also, again, I ended up not using that either. Alright, so instead of using IUV now, let's see what happens when I use my UV coordinate, the one that I got from all my calculations. Don't spoil the surprise, please. Come on. Okay, it took a while to load, but something is off. Yeah, it tries to reflect things, but it doesn't quite do that. So let's see if I missed something. Well, let's first try. Wait. Am I missing something? Midpoint distance. Should be right. Let's calculate some stuff. Alright, let's get a vignette thing going on here. So that I got straight from Unity's SSR implementation. And not working. All right. Oh, really nice. Ability also is gonna be multiplied by a Fresnel, which is gonna be a saturate dot the ray direction, which is basically the wall space view direction, with normalized wall position minus camera position. Sorry, this is basically wall space view direction. This is the reflected direction, so we're getting a Fresnel from that. And another mask for our visibility could be this one. I'm gonna tell you about it in a bit. Right, it's a length spring to walled post. Thank you. UV coord minus the wall position divided by the max distance. This is basically to fade out with the distance. Another thing is, with the smoothness, but just say that to be 1. And this is also to make sure that the ray doesn't bounce off outside the limits of our UVs. So, if it's 0 or if it's less than 0 or more than 1, and the same thing goes on for the Y. And now the color could actually be the lerp of color, and background color with a saturate visibility. Let's see where this takes us. It doesn't quite seem to work, but we'll find out why. And it's kinda trying to do something. You see that? It's kinda trying. Let's see if my values are all alright. And I have the same exact values as my test beforehand. But you know what, just to, you know, make sure everything looks the same, I'm also gonna add this hash function, which I can use, as I mentioned, to jitter my ray around based on the smoothness, which again, right now it's 1. So the ray direction here, ray direction is gonna be 33 volt pulse XYZ multiplied by 10 for some reason, minus 0.3, 5, multiplied by 1 minus smoothness. Is this gonna help at all? It does not. Alright. Let's try and see why that could be the case. Just hold space, camera pause. I think it had an issue with... No, there wasn't an issue with hold space camera pause, right? No, that should work alright. Screen the wall pause. Hide the tray. Sorry. Screen the wall pause on the tray. IDUV and getting the world normal. The ray direction is normalized, reflect, normalize, world pause minus cam pause, normalize the world, the world normal. Resistance 0, distance travel 0, UV core, IDUV, visibility equals 1, depth thickness. Distance travel. Let's say that I'm not using no, I am using that. Okay. Wall position plus ray direction, upper distance travel, screen to wall pause, either tray, wall to pause screen, wall to screen pause, whatever. Yeah, ray position, project distance, projected pause. That's gonna be this thing. Post beast, okay. Oh, there we go. It's not ray pause. It's ray pause beast. All right. Well, yeah, there we go. All right. Yeah, it was a bit of reckless coding. Hey Jay, welcome to the stream. It's going alright. I just got my reflections working. And yeah, there is some artifacting going on. There's plenty of artifacting going on in some cases. And you know what, just to make sure. Yeah, no, we're gonna have those. Actually, yeah, that makes a lot of sense. So, annoying thing about screen space reflections, right? As I mentioned, you cannot reflect what you cannot see, right? So here, you know, you have this beautiful white box, which is being reflected on the ground, and it's awesome. But the thing is, you know, when you have something covering that box at the point where the reflection should be, you're not getting a reflection because things no longer in your scene. So yeah, tough. There's no good workaround, to be honest. And screen space reflections aren't, you know, supposed to look perfect and accurate and whatever, right? So here I have a normal map, right? If I smooth everything out, like you can see that there are some minor ray marching artifacts here, because you can see like from the stepping going on. You can see that there are some artifacts there. You can see that like there's this thing here that because I'm hiding this part of the column, it's not reflected properly. All that stuff, right? You will get those stuff. There's no way around them, to be honest. But screen space reflections, as I said, they're not for accurate reflections. They are for muddied, normal map, enhanced reflections. Like, yeah, here I have a pretty intense normal map, and yeah, these artifacts here, I mean, you can barely see them right now. And as I mentioned also on my demo on the tweet, I'm not doing anything extra here. I'm just rendering the same final picture with just modified UV coordinates, right? So I also promised the thing with the roughness. Right now you can see that it's not with the smoothness. Right now it doesn't change based on the smoothness, so let's change that. As I mentioned, I have a way of getting the smoothness of my scene. Thank you, deferred rendering, for that. So let's get the smoothness to be and so down. Yeah, I mean, yeah, if it's screen space reflections, yeah, I mean, you can only have some cool looking reflections at very specific angles and moments. And you know, the more you muddy them, the better they look. That's just, you know, you cannot expect to have good screen space reflections everywhere. But the thing is that this method is pretty fast, and you can still get some real-time environment aware color changes in your scene. Ray tracing is going to play this in the coming years. Yeah, pretty much. Yeah, that's the point of ray tracing. But until then, you know, this is a nice approach still. And again, even if you don't use that in your game, just I was really happy for myself to actually figure it out intuitively and, you know, making it make sense to me, because again, it's an effect that I was looking at years now and, you know, didn't really understand how it works, and now I do. So, you know, I just wanted to pass that forward, and hopefully, you know, this was somewhat understandable and intuitive for you as well. So let's get the smoothness. Again, this is stored in the first gbuffer on the alpha channel. So now now. If I increase the roughness, you can see that with like, you see that the ray is getting more diffused, and it's just a silly little trick where you just jitter the ray direction, so you basically simulate diffuse scattering. And I fade it out with the amount of smoothness, so it kind of looks natural. But as I mentioned, yeah, mates, I cannot even imagine your pain. Haven't dealt with mobile for a while, and yeah, I don't plan on going back soon. And so yeah, this also looks very noisy, but if you throw in like some, well, temporal anti-aliasing just makes things worse, but like some AA, and also just turn the normals up, then you get some reactivity on your materials, some real-time reactivity. And if I also hit play, I think that the stream might drop some frames here. Whoa! Yeah, it dropped all the frames, but the thing is, yeah, it's all real-time, and it, But as I mentioned, this is not the intended purpose, so that's something cool that I will want to try out, and I want to see how it plays out. All right, so bear with me for a while. Like, all right, let's return load for i.qv00, right? This will give us the default screen UV coordinates. That's awesome, right? Right. Let's now get the lerped coordinates, our reflected coordinates, UV coord, based on saturate, just visibility, and bring that here as well, and saturate visibility. All right. So now that will give us something interesting. Whoa, I'm dropping frames, but do you see what's going on here? Let me remove that. Do you see something interesting going on here? Why am I dropping so many frames? Not doing anything. So can you notice where I'm getting at? These are what our UV coordinates, the modified UV coordinates from the SSR look like, right? You can even though these are coordinates, you can still understand this shape here, that it's that jumper thing, or that I can easily find where things are. So the cool thing again is that we have the modified screen coordinates. So let's try something else. Let's try something different, though. I think that I will pretty much more or less get the same result, but I want to see it happen, right? So instead of that, I want to return the float for color. No, sorry, float for with the UV chord. I don't need the blue channel and the visibility, right? I'll just return that. Interestingly, you can see without the visibility masking, you can see some other extra elements. And you know what? Maybe the visibility masking is a bit too austere, too conservative, and we're hiding some stuff that we could get, like without the visibility check. Like if we said, return a raffle color. Yeah, no, way too noisy. That's also because of all the stream does not like that. Yeah, no, way too noisy. Just way too noisy. Never mind that. So we don't care about that. We just want like the UVs. So if now I get that, right? And let's say awesome. And do all the basic and say a circle and the texture get temporary. No, you know what? Let's just do that here. And you know what? Don't need that. Don't need that. Don't need that. All right. Get temporary context source. Yeah, just kinda not. Crypto. Alright, context height. Okay. Alright. Always remember to release your temporary render texture, because this is gonna eat up your memory. So if instead I, let's say, do split full screen triangle over to FStar codes RT, right? And context command, split full screen triangle, just context source, context destination, and everything goes back to normal, right? Right. But the thing is, now I can go here and say there's set global, or I think I can do the context command, set global texture, and call this global XSR UV chords. Let's copy that. Let's go something. All good, all good, alright. Again, dropping frames. That's weird, that's annoying. Anyway. You know what? Doesn't like full screen windows or like larger windows or whatever. Okay. And now I happen to already use a custom deferred shader. And the reason is that if I want bandit lighting, I can just change the alpha of my lights. That's a cool little experiment that I've been abusing lately. Anyway. So what if, let's say that instead of this result here, I return texture 2D, it's CG, right? Right? Yeah, it's CG. Texture 2D and just this with I dot or just UV. Yeah, I get the UV somewhere, right? Oof. Oh yeah, sorry, I have to declare that. So gimme, come on. Oh, well, sorry, brainport, alright. Gimme, yeah. Kinda, okay, yeah. I know what's up. Okay. My intention here was noble. But the thing is that post processes are automatically being. I mean, can I change that context? Command event. Romance and sound generate memes. Yeah, so the thing is that the post-processing event happens after the gbuffer rendering, so this texture doesn't exist when I want to the deferred rendering to happen. So can I actually set when I think I have a crap. Before gbuffer, before, I mean after? Yeah, after gbuffer. Okay, No. It's killing my frame rate. So yeah, a weird issue around it that popular in the feature was when I had a custom render feature followed by a render object feature, the sorting of the render object was messed up because not covering over the depth target from a previous pass to the next pass during cleanup. Oh boy. Yeah, I'm getting into that stuff with custom render passes. Yeah, it's weird. Camera. What if I do this? Wow, that's... Do I have quick context? Camera. Execute. No. If I set it... Oh yeah, this would require, yeah, proper command buffer work, which I'm not too excited for. This won't work, right? Yeah. The bot, right? So yeah, my point was, in any case, that if I could, which, you know, I should be able to, and I could do that, you know what, just out of curiosity, I mean, out of curiosity, if I go in here and post-processing, runtime, effects, screen space, reflections. Basically, that's what they're doing here. They, with Unity's implementation, just obviously more complicated than what I'm doing. And then again, okay, I'm not gonna do it. It's a bit overkill, but here's the thing. Okay, screw all that. Screw all of that. Here's the thing. the whole thing process of deferred rendering is that it's basically a post process, well, not a post process effect because it is a process, but it's essentially grabbing all the screen space textures for the albedo, normals, smoothness information, metallic information, specular color, all that stuff. It's calling this magic function, and boom, you get standard lighting based on your screen space textures. So if I wanted to, but it sounds so messy, don't want to do that. But if I wanted to, I could basically just copy all that, like these passes here, and put them in my shader and call those passes. And instead of these UVs, I used my screen space reflection UVs, and yeah, it would basically get the proper result. But yeah, I'm not gonna do that. It's just I think it's enough for what I had in mind for this effect and for this stream to just wait, no, that's not what I wanted. I wanted this, and I wanted destination, and screw that, and that should put us back in business. All right, in screen space reflection business. Yeah, I think that's the end goal for this stream, and I wouldn't want to go further on. It's confusing because you have shader passes and SRP passes. Yeah, for the custom ERP render passes. I can say they're pretty powerful. I actually kind of like them, but making them all work together, it's a bit annoying. So yeah, almost 2 hours, not too shabby. And yeah, to be honest, there's more than one could do for this. Like, honestly, you know what? Let's you can actually get like a lower resolution texture for this. Texture is temporary. That's not perfect. Please, yeah. Do that. I don't want that though. And you know what? No, actually, no. Screw that again. You could put those UVs on a lower downsampled buffer, and yeah, then, or just the reflections, you can downsample them and blur them and all that. But yeah, whatever. This is the gist of it, all right. And I just wanted to share this approach because I felt it was very intuitive to see how you can visualize the rays and get the ray marching, and I don't know, it felt intuitive to me. And I hope that it will help you do some similar stuff. And yeah, I think I'm gonna close the stream around here, almost before the 2 hours. I don't know if you have any questions, but yeah, I'll upload this to my YouTube so everybody can see that and reference that, and I'm probably gonna be one of the people that would want to reference that because I won't remember everything. And yeah, hopefully I will come back with another stream pretty soon. So thank you all so much for joining. I hope you enjoyed, and I will see you in the next stream. Bye bye.